there are a few new people also. So what my plan was today is to give an overview, at least of where we have come from and where we are, so that you guys can all, because it's very important in mathematics to summarize the things, okay, and just see the main dots, and then you can fill in. Otherwise, you can get overwhelmed by all that what's happening. Okay, so I'll give an overview, and this will help to tie up all the results, and it will help you to see the way we are developing this topic. Okay, so this will be a brief overview first. So let's do that first. Okay, because then you will be able to collect all the results. You will see if there are a few things which you have to still try to prove in between and so on. Okay, so that's why. Okay, so what did we start with? And in between, I'll maybe ask some questions so you can fill in the gaps. Okay, so just to put things into perspective, let us ask this question. Okay, what did we start with? Okay, so we started with, so when we started this topic of mean value theorems, okay, we didn't actually just start it randomly with mean value theorems. Okay, we started with looking, so given graphs of functions, we started with looking for tangents. Okay, we started with looking for tangents that are parallel to chords. Yeah, this was really what we were searching for. Yeah, we were looking for in what situations, what are some sufficient conditions that would help us to get, tangents, okay, parallel to chords that are given. Okay, so in graphs of functions or graphs of curves even. Okay, so and then if we draw a chord, then can we guarantee a tangent that is parallel to it? Okay, so we were looking for situations. We were trying to find places in which such things, or where such things happen. Okay, so basically we were searching for places where this happened. We had discussed why this is important. Okay, searching for places where this happens. We did find a few places, and I will not mention the details of places, but I'll just say it in the form of results, right? We found Rolle's theorem, and obviously, so this is something that we all know, and we found the Lagrange mean value theorem. Yeah, so these are the two theorems that we know which guarantee. Okay, so this is, so they affirm you that there are some places, namely graphs of functions. Yeah, graphs of not just functions, graphs of differentiable functions. Okay, differentiable functions. Yeah. That if your graph is a graph of a differentiable function, then given a chord, you will always find a tangent that is parallel to it. That's what geometrically it says. Okay, but remember, it only applies to graphs of differentiable function. It, for example, will not apply to something like this, though you may say that it looks like there will be. Okay, but you'll not. I mean, if there is a description, so you see this S kind of figure that I've drawn, right? This S that I've drawn, this might be given in the form of an equation as a subset of R2, as an equation whose solution is this and so on. But this is not the graph of a function. So we cannot directly invoke these two results to conclude that for any chord, there will be tangents parallel to it. Okay, there will be at least one tangent parallel to it. Okay, so then we tried to look for other places. Okay, so this is for graphs of differentiable functions. Okay, so what is that theorem that guarantees, the occurrence of this phenomena, tangents parallel to chords, in a larger family of curves? Okay, so in a larger family of curves, what is one more theorem that guarantees these things, guarantees a presence of tangents that are parallel to chords? Okay, family of curves. So can anybody tell us what was the next result that can help us to enlarge this set of places where this phenomenon happens. Yeah. So if we want this phenomena of having tangents, given some chord having tangents parallel to it, then what is that? What is one theorem that guarantees such things will happen outside the realm of just graphs of differentiable functions? Yeah. Cauchy's mean value theorem, right? Can you describe more how Cauchy mean? So we obviously all of us know the statement of Cauchy mean value theorem, but can we describe how this is really important? How Cauchy mean value theorem, maybe someone else can also say, I would appreciate it. Okay, how Cauchy mean value theorem guarantees the above and in what setting? Then we can say that we understand Cauchy mean value theorem, at least from one aspect. Because there will be hundreds of mean value theorem that you will encounter depending on where you are working, in what area. So that's why it's important to understand why we are looking at these things. Yes. So anyone have thought about, or you can just think, if you don't cannot answer the specific, just think what is the significance of Cauchy mean value theorem. Okay, maybe I just also write it out. Just obviously we know this, but point is to just, there is a C between X and Y. How does this guarantee existence of tangents parallel to chords in a larger setting? That is the whole thing. In a larger setting, outside just graphs of functions. Yes. Mm-hmm. Mm-hmm. Yes. Okay. So let me just repeat just 1 second. Huh? So I'll try to say it in a slightly different way. See, so we are trying to discover these things one by one, and so that we can connect them all. Okay, it is because in analysis it's not hard to actually prove things usually, but it's hard to know what to prove and what. So I'll just and then I'll come back to whoever was saying about this. Okay, see, initially, see, whenever you have the graph of function, let's say, okay, and you have a given chord, right? We are always looking for a tangent vector that is parallel to it for all sorts of reasons. Yeah, one being that it helps you to understand how the derivative of a function controls a function. Okay, so there are a lot of like knowing information at two places, and you can understand what the function can or cannot do in between, things of that nature. But in any case, point is, we want this geometry phenomena to happen, and then we are like, okay, when does it happen? It seems like it happens in a lot of places. We had seen earlier in half chord lemma and so on also, but let's not go that much back. And okay, in a more standard setting, we have the Rolle's theorem and Lagrange mean value theorem, which guarantee that, right? But the limitation of these two theorems is that they only guarantee you this in the case of graphs of functions, right? If this is a graph function, then only given any chord, you will have a tangent parallel to it, right? Then only they guarantee this. They do not guarantee, like you cannot use this, simply put, you cannot use this theorem to say that given this chord, there will be a tangent like this. You cannot say it. just using this theorem. Maybe you have to make some modification, cut, paste. We will see those local things like implicit function theorem and all later, but these things, right? So, but our eyes tell us, right? Our intuition tell us that it should again happen. It should happen for these kind of graphs also. But what do you mean by these kind of graphs? If this is not the graph of a function, as this red thing, this S as a subset of R2, if it's not of a graph, it's not the graph of a function, then what is it? I don't know. Okay, just a subset of R2 a priori, okay? Then we ask ourselves, okay, graph of function is one thing. What is the next best thing? After graph of a function, geometrically speaking, what is the next best thing? Okay, and that is those subsets of R2, which are parameterized by not one, but two functions. This is a subset of R2, right? So if you, I mean, instead of R, if you just take, let's say, let's take a comma b. Okay, then a comma b to R2, if you take this function, right, then this is a subset of R2, right, which is not the graph of a function, okay, because x is not going to y, not, maybe it's not the graph of a function, but it is definitely something that is parameterized. Like you can understand theta going to cos theta comma sin theta, you get a circle, right? So this kind of curve, okay, and now we are trying to see if in this kind of curve, which is very close to, which is very well behaved curve, right? So when t ranges from a to b, then I don't know what you get. You may get something like this also. This is a standard way in which is drawn usually, so I'm just drawing it like that. But this is not the graph of function. And now let us sit and think. I mean, now let us listen actually to what I think someone was saying about how we can guarantee the same phenomena in this for these kind of graphs which are parameterized. This is called parameterized by t, right? Parameterized by t. Okay, so that was again just I basically repeated myself, but it's a different way. Okay, so whoever was saying, please continue. Yeah. Yes. Yes. Yes, slope of this line is, as you're saying, it's GB minus GA. Yeah, you could have taken same thing and FB minus FA. That's clear. Because this point is this point. So this is not the graph of function, right? So this is FA comma GA. This point. So maybe that's not the right way to say. This is P, this is Q. Then P is obviously FA comma GA. This is very often seen in physics, like this kind of thing, right? And then Q is FB comma like velocity or position vector with respect to time and so on, FB comma GB. Okay, then yeah, so this is the slope of the line. This is the slope of this chord. Okay. Yes. So you see what he's doing is once you are able to describe this curve using this parameterization, then you translate the geometric intuition that you have of having a chord or having a tangent parallel to the chord, you translate it in terms of equations. And when you translate it in terms of equations, this is what you get. That this is what, so I'm not yet saying this is true. This is saying this should happen. This is what should happen. So you see, it's all about writing it in the right language. Yeah, going to the right family or going to the right family of objects and then writing the intuition you have in the right language and making the claim. Obviously, if the proof is very simple. Yeah, proof you can just do. Cauchy mean value theorem proof is straightforward textbook proof. Okay, so from here it's easy. But you see, Cauchy mean value theorem is not something. Okay, maybe in Cauchy's time it was a surprise, but if you study this thing in this way, if you think about it in this way, it is just the next natural thing. Okay, right? So that is the thing, and yeah. So naturally, the next question that comes up is, given a subset of, this is what we wondered about a bit, right? Given a subset of, so what was next? What did we do next? This is all that you've already done, right? what did we do next? Yeah. Yeah. So next you see there are two kinds of things. There are two ways in which one can move forward. Okay. See, one way is to now that we understand that, oh, if you have a subset of R2 and if you can parameterize it, then you are very well off. Yeah. So then that's why then the next question comes up, or the next natural thing to try to do is find parameterizations of subsets of R2. Yeah. Maybe it can be given in the form of an equation. It may be given in just the good old set builder form. And you have to see if you can parameterize it. You have to see if you can describe it, right? For example, if it is just the graph, if it is just this equation is given, obviously all of us can parameterize it, right? Just the x equal to cos theta, y equal to sin theta. So that theta going to cos theta comma sin theta is a parameterization. So we did talk a little bit more about this thing, and then we stopped and didn't go further. We will pick up that later on, okay? So this will be find parameterizations of curves, and then ask if you can find polynomial type parameterization, or prove you cannot find parameterization, and those kind of questions. Okay, so those are interesting questions which we'll see later. But next, but we took a different route, okay, which is more in the spirit of analysis and geometry. Okay, I mean more in the spirit of differentiability and the kind of things we are doing. Parameterization is slightly different topic. Okay. So when you're dealing with Rn, then so the problem happens when you're dealing with Rn is, see, once again such a phenomena should hold, right? So if you have again a curve, some surface, okay. So again, if yeah, so if you have a surface and hold on, so then the surface would be described as T going to F comma G comma H or something like that. Okay. And then if you take a chord, yeah, so then the problem happens is that, or rather this will not be a chord, it will be a plane, right? When you take a plane, then you the biggest problem is that the slope of this plane is no more a number, right? One number does not describe the slope. So if you take a chord in 2 dimensions, that is just one number. That's just one slope, one number, fb minus fa by gb minus ga, right? But in 3D, at least already in 3D, it's not a number anymore. And then in the same way, the slope of the tangent is also no more a number, right? So then it is a vector. Yeah. So in that case, there are some results which, yeah, so then it gets a little complicated, because then the slope itself is a vector. Then there are some not equalities but inequalities, but that's already difficult to state. So that's something like this is less than max of the derivative of something of this form is there. So the derivative itself is a vector, so you have to take the norm of these and take the maximum, something like that is there. Okay, and then there are some variations in the determinants. Yeah, but that is already there. But problem is that one has to first understand how to define this slope of chords properly, and then okay, and what is the definition of derivatives of function from R to R2, then only one can, yeah. So before that, but again, yeah, such phenomena, as you can see with your eyes, already should hold, and then if you just set up the right language. But that gets a little complicated. Okay. Right. So coming to yes. No, but you cannot parameterize a subset of R3 using one function, right? You will need 3 functions. right? So yeah, all these three are one variable functions. Okay, all these three things are one variable functions, but there are three of them, and the slope would include two quantities. Okay, the slope would include two numbers, right? It would include maybe f and g in one place and then g and h in another place. So it will still again be a vector. And then then how do you define derivatives? That becomes a real question in R2. So that is problem. Okay. Yeah, but again, such results will hold. Okay, though myself I have not thought about it beyond something. Yeah, but one has to define. Yeah, but you cannot escape the fact that you need two numbers or a vector to define slope. Yeah, because two pieces of information are there. You cannot do with one. Okay. Yes. Yeah. So let us stop this parameterization thing. So and come to this other thing, right? Where we were trying to generalize things in a slightly different direction. Okay, and how did we find inspiration for that? We looked at some basic implications. We looked at some basic implications of mean value theorem. Yeah, basic implications of mean value theorem. Basically, the essence of mean value theorem is that how the derivative controls the function, right? This later on generalizes to Taylor's theorem and so on. And the statements you can see, or probably some people, or if you've seen already Taylor's theorem a little bit, it is like f in terms of the derivatives. Yeah, so it's all about how the derivative controls the function. Okay, so that was the essence of the mean value theorem. But some concrete results we saw, right, where f dash equal to 0 implies f is a constant. Yeah, so then we looked at results like these. Okay, so we looked at some implications of mean value theorem, and then we asked, okay, when can these implications hold, or can we find a larger class of, larger place where these implications can hold? Yeah, so when can this hold? When can this hold beyond derivative condition? Yeah, so then we are trying to not generalize the mean value theorems, or not find larger family of subsets of R2 which are parameterizable, or finding techniques of that, but we are taking some implications and we're trying to see when they can hold. So basically, the power of mean value theorem is good, but also that results can still hold even if things are not differentiable. Okay, so this is the kind of questions we asked. And so when can this hold beyond the derivative condition? So can anybody has anybody thought about this, or if you remember or thought about what are the cases outside differentiability condition when this still happens? This is one of the things that we had done, and maybe other things if you have thought about. So we are looking at some implication, and then we are seeing if we can generalize it. So if this derivative condition is not there, yeah, then still can we state a similar result even then? Absolutely, yeah. Yeah, right. So if f is, so just for simplification, if f was a function from a comma b to r and right differentiable, and I'm not going to define right differentiable, you guys know it. Okay, right differentiable, only right differentiable, yeah, only right differentiable, and one can use the notation is equal to 0. That again implies that f is. Please just go back and again think of, try to prove this again if you have not. Okay, and for those who are joining for the first time, try to prove this. Okay, this is a very good exercise. Okay, that if this looks like a trivial, maybe simple, but it uses some deep properties of the real numbers, supremum and so on, right? So in a new way, because you don't have that good condition of derivative. Yeah, so f is only right differentiable and the right derivative is 0. Okay, and I'm not going to say more now, as we have already said about this. Then also is holds. Yeah, and similar results are there, other results are there like this, but we saw this, right? Then we said, okay, right differentiability seems to be a very good thing. Then we went down this lane and we went to, yeah, and also I had given some homeworks in parameterization which I have not discussed yet. So I'll do that when we revisit parameterizations. Revisit meaning do different, because parameterization is a topic that lies at the border of number theory also and so on. So we can discuss it that time. So here, what I was saying is, we saw that right differentiability is a very good condition. So we introduced a notion called semi-differentiability. Semi-differentiable. Now, semi-differentiable means that, obviously, it means that right and left differentiable. Okay, not saying that they are equal, but just saying that they are. Okay, so then we saw this. We saw that when right and left differentiability both occur, then we call such a function is semi-differentiable. Okay, and semi-differentiability had some very nice implications. It implied continuity. Okay, now having proved this kind of result, what was the next question we asked? We asked, okay, I mean, we have proved this, but is it of any use? Are there any interesting functions or naturally occurring functions which are right differentiable and not differentiable, or which are semi-differentiable in even, meaning right and left differentiable, but not differentiable? So is this a good theory? Yeah, does this theory have a rich number of rich examples, right? So that's what we asked. Any natural examples of, obviously you can always construct arbitrary examples, but natural examples of semi-differentiable functions which are not differentiable. Yeah, so can anybody? Mod X is certainly one example, but in general, yeah, in general, mod X is obviously a good example. In general, it is the convex function. The mod X is obviously a convex function. Yeah, convex functions. Okay, so convex functions meaning don't assume differentiability or anything. Convex function just means convex function, right? It just means that the graph looks like this, but don't assume anything about differentiability and so on. Yeah. Convex functions, the definition is obviously should be there. It is that this thing holds, right? No, so this will become the other way. We want the function to be below the average. You can obviously interpret this, but obviously you need the condition that this has to add up to 1. Yeah. So graph and this, you can see that they are the same. Okay. This is the definition. Okay. So then we looked at convex functions, and convex functions we found were semi-differentiable. Yeah. And this is what, and this is crucial. Yeah. Because being semi-differentiable means, and that's what we used. Yeah. We used semi-differentiability to show that they are in fact continuous. Yeah. So convex functions are continuous. And the way we did it is using semi-differentiability. Yeah, convex functions are semi-differentiable because they are, and please try to prove this again if you don't know, if you have not done it. Yeah, semi-differentiable, hence continuous. So this is a very interesting exercise to do if you have not done it. Yeah. So these are the things that we already say, or already said. Okay. So now let us try to say something new. Okay, because today I'm just saying repeating because I already missed the first 20 minutes and today it's mess, but I'll try to make it up later. But this is convex functions are semi-differentiable and hence continuous. But let us try to see something new. See, semi-differentiable, as the name suggests, right? Semi-differentiable functions are kinds of functions which are susceptible to being differentiable. Yeah, they will tend to be differentiable. They will tend to be differentiable. Okay, but obviously they need not be differentiable. That's why I have a different definition. It's a semi-differentiable function. Yeah. So yeah, so the meta statement is that convex functions are susceptible to be differentiable. Okay. We can put this in another way. We can say convex functions are almost differentiable. Okay. Convex functions. Again, this is just at this point maybe just a vague statement, not a mathematical statement, but we'll prove something mathematical now, and it will become convex functions are almost. Obviously, we did some other things, but yeah, let's do this now. Convex functions are almost differentiable. more analysis. Okay. This is a statement which we want to give mathematical meaning to. This is a statement that we already feel is correct. Yeah, because you see convex functions are semi-differentiable, they're right and left differentiable. Okay, now you have to prove it if you have not proved it, and it had good implications. But now we want to say that convex functions are almost differentiable. In what way? Anyone has thought about this? So we have seen the connection of convexity, continuity, semi-differentiability, weaker convexity, the midpoint convexity that we had seen. But now we are investigating convexity and differentiability, not just semi-differentiability. So this is a statement. What could this mean? What could this mean? So let's say that f is a function from 0, 1 to r, f is convex. So for all of this, lambda 1 f plus lambda 2. Yeah, just let your imagination just think what could this mean? It could mean several things, but is there anything, one thing that you can think that this could mean, which you can put mathematically? Okay. So that is one interpretation. Let's see if that is correct. Yeah. So convex functions are differentiable at all, but this just means the same thing, obviously. Yeah, all but finitely many points. Or, it is not differentiable at only finitely many points. So is this statement correct? Or can anybody give a counter example? Obviously, remember, I have restricted it to 0, 1 so that you don't create some not good examples. So that you don't escape. Is the statement correct? This is a question mark, obviously, it's not yet. We're just trying to explore. So what do you think? Do you think this will be correct? So see, obviously, first of all, let me make it very clear. I suppose it's already clear, but still I'll say it, is that convexity does not imply differentiability. So can anybody just quickly give an example of a function in 0, 1, which is convex but not differentiable? And that is very easy. Can anybody do it? We want just an example which is convex but not differentiable, meaning that it just at least one point it is not differentiable. Yes, simply right? Mod of x minus half. So just something like this. Mod of x minus half. So this is very simple. So convexity obviously doesn't imply differentiability. And see, simultaneously, let me also explore a related notion which is called strictly convex. Okay, because I'd given a problem which is very convex, a very convex problem, right? Which I will discuss maybe next time, or some we'll see. Yeah. Obviously, very convex functions don't exist. That was what the claim was in that problem. But I'll share it with for those I have not shared. But let me just so this is convexity. But let me also simultaneously, because so can anybody give an example of a strictly convex function? So I'll just define it. Just the inequality will be strict. But it's not strictly convex. So you may say this is slightly cheating. Okay. But let's see. Strictly convex. This is not strictly convex because there's a line. Obviously, and if some things are not clear, you can just say, okay, if I need to say it now, I'll say, otherwise I'll refer you to where it has been done in the past. Can anybody give an example of strictly convex function which is not differentiable? How would you make such a function? Because these small examples, these are in like MCQ type, but it will help your intuition a lot, maybe. Yes. Oh, sorry. Yeah. So I'm looking for an example of a function which is truly convex, okay, which is strict inequality here, okay, truly convex, but not differentiable. So the example that has been given here, yeah, it is convex, but it is not strictly convex, right? Here there will be equality. These are all equality cases because there are straight lines. You can obviously. Yeah. So can anybody say, especially those who have not said it, or just give a try, or just what you're thinking, because this is a discussion to start with. I don't know, or can there be? So maybe so you're saying it's not possible, but think, let's see, or what? And remember this convex. Okay. So e to the power mod x minus half. You just raised to the power e. Yeah. So you can compose it with this thing, and obviously it become right. So e to the power mod x minus half. Yeah. You can check. You can just check that this will not. So you can obviously check this will not be differentiable at half. Yeah, I guess all of you can do that. Okay. I mean, I'll have to also check, but it's obviously, it seems to be correct. Yeah. Any constant, that's right. Any constant. You're right. Any constant other than one, it will work. Yeah. And so this is the thing. And let's just do a quick check. So at 0, it is e to the square root of e. So somewhere here. And at half, it is 1. So here. And then at 1, it is, wait. Yeah, here, right? So you see this, this has a sharp edge, if you want to call it a sharp edge, whatever, but in the end of the day, it is not differentiable at that point. Something like this. Yeah, not differentiable at this point, obviously. Okay. So in this manner, you have, so we have created an example of a convex and a strictly convex. So these are the ways to compose functions to create. Yeah. Sorry. Okay. So my point now is that in this way, you can construct convex functions which are not differentiable at finitely many points. Okay, so you can make this example. So to do this for homework, oh no, so I should not circle, it may give a wrong impression. My point is that just do the strictly convex example, or both. No, but you can easily do it now. Okay, just have to squeeze and so on, right? Find strictly convex function not differentiable at finitely many points. I should just say n points, right? It's a better way to say it. At n points for any n. Please do this. Yeah. For any n, you can find. You can just extend this example. Okay. And try to. Something like that will work, right? Yes. That's right. That is right. That's right. But now let us actually come to this claim. Is this claim correct then? Yeah. Is this claim correct? That okay, 4 point. Okay, yeah. So let me just state that. Okay, so currently this is what we are doing. Yeah, we are trying to understand if a convex function can be differentiable at infinitely many points. Let me state that question first clearly, because now we have already answered the finite case. Yeah, or rather form of we have given. But can a convex function, anyway, strictly convex function, be not differentiable at infinitely many points? Okay, this is this is the question. And just to recall, we had this alternate definition of convexity. Yeah, easy to prove. Again, if you have not done it, we did this in the class. So for those who joined us from the first time, try to prove this. Okay, convex function. Yeah? This is the other definition, which is basically, just to repeat, it is just motivated simply like this. You can take this just for comma p, and then you can take any x1, x2, x3, x4, and you see if the graph is convex, then if you take x1 and x3 and you take that slope, right, that is going to be less than the slope of x1, x4 that the line or the chord x1, x4 makes. Yeah, this is obviously looks true, and but this can also be taken as a definition of convexity. Let us also write it out. So yeah, I mean, well, you guys can think about this. Is it possible for if for those who know this definition? X3 minus x1, x3 minus x1 less than. Yeah, this can, oh God, what happened? Yeah, this can also be taken as a definition of convexity. Try to show that they're equal, but don't try it now, just assume it and maybe think about this. Is it possible for a convex function? So don't think about strictly convex maybe. Just think about, can you make a convex zigzag some kind of function which is not differentiable at infinitely many points on 0, 1 and is convex? And if this helps, then you can use this. Okay. And if the question is not clear, just ask. I can. That, yeah, maybe you can use that to construct, but then you have to prove, or you have to at least say a method. Yeah, but non-differentiable doesn't necessarily non-differentiable. See, from what you already know, the convex functions are continuous, right? So there cannot be a jump or anything like that. So or there cannot be a vertical slope, right? Those things should not happen. especially on a closed interval continuous function, right? So non-differentiable will mean kind of sharp edges, where this also counts as a sharp edge, obviously. Yeah. Usually that's what it will be now. Yeah. Because see, this is both left and right differentiable, right? So you can understand. Yeah. I mean, so the point is that at any point, tangent will exist. Left tangent, right tangent, both exist. The problem is they are different. That is the only problem, isn't it? Right? So yeah. So here in this case, non-differentiability means exactly sharp edges, if that whatever that means geometrically. Yeah. Hmm. That's that maybe can be also done, but can we? But there are much simpler things in between, which I think countable set. Okay, but essentially, I think you have already said the answer, but now you are saying something very different. Countable set that can be done, but that's see one very simple thing is just this. Yeah, you guys, as I said, just think in an organic way. Think about just this first. Okay, oh, you can just do something like this. Now write the definition for this. Write a definition for this kind of function, which will have infinitely many things like this. See, you can't do zigzag. This is not convex. It's not convex, right? Not convex. Because this part is convex, this is concave. I mean, they are different. Okay. But this will work, right? This will work. Write a definition for this kind of function. Do it on your own. Write a definition for this kind of function, because this is just an extension of what someone at Mahima, I think, said already. And then someone said about half and half square. Just mix those two things and write a definition for this. Okay, you will get the answer. Okay, that is the thing. Now, how to do this? Mix it with what I think someone said, e to the power. Mix those things and you will get a strictly convex function, which is not differentiable at infinitely many points. Okay, so the rest is just homework. Just work the details. This is these are the ideas. Any issue, any question with these ideas? Then I'll come to what Raghav is saying. That is something more general, which we can use to prove something, I think, more. But I did not ask that, but that's certainly a bonus if one can do that. But is this clear, or is anything here which I should repeat? Right. Okay. So yes. So I think that if you so certainly it is possible. Yes. It's possible. Now, from what Raghav is saying, it's actually more is possible. Yeah, actually more is possible, and this is the following. Now, I will not. Let us. I will not go into the details of it, okay? Because suddenly we'll go into a different thing, okay? But let us just say it, okay? Given any, so any is very. So this will, so see, there are several levels of many or almost, right? Finite is obviously not almost. But yeah, that's what you're trying to say, not finite. But not finite is certainly almost, but not differentiable at infinitely many points. This is what we have said till now. Okay. One second, yeah. So we have proved that a convex function is not necessarily differentiable, okay, at infinitely many points. Okay. Before going further of what I was going to say, see, this may seem, and we have answered this in affirmative. I mean, yeah, there are details to be worked out, which you should do. Okay, but we have answered this in affirmative. Now, this might make you think, oh God, then almost differentiable seems incorrect. Okay, so I will come there. Okay, even though convex functions are not differentiable at infinitely many points, but still that infinite set we will show is a small set compared to interval 0, 1. Okay. And I'll also try to say that in the language of areas, means the area of the set on which it is differentiable or not differentiable is 0. We will see that, but before that, I'll just do a problem on areas of sets, which is a more relevant, very, very relevant problem. And then I'll do this next time. Okay. But again, let me come to what we have taken. So roughly speaking, you have got an idea of an infinite set on which it is not differentiable, even strictly convex and not differentiable. Okay. But from what Raghav has said, so you can basically do this for any sequence. Given any sequence or any countable set just means a sequence, just something that can be listed one by one. Eventually everything can be listed in that set. That set is called countable, enumerable, whatever you want to call it, okay, or just sequence. So given any sequence, see if you have any sequence, so one can make, okay, obviously the sequence is 0, 1, can make a convex, even strictly convex, yeah, strictly on. Now this is not, so this is more stronger than just infinitely many points, okay, because of some geometric reasons, because an infinite set may not be geometrically interesting, okay, because if you take half and half plus half square, half plus half plus half plus half square plus half cube and so on, this is an infinite set, but it is not a very interesting set. It only has one limit, that is 1, okay. But we can have some sequences in 0, 1 which can sort of fill up the entire. So that's why this is a more stronger thing, but at the same time, it's slightly more involved. We can make a convex. Actually strictly convex even. Okay, if you strictly convex function, okay, not differentiable on even exactly. Okay, on exactly, I would say. Wait. Yes, no, let me not say exactly. I might be wrong somewhere. Yeah, there are some details maybe. Yeah, so not differentiable on this. Okay. Try to maybe think of a way, but it's a little more complicated. Okay. Okay. Well, why is this stronger? Because you can take countable sets which are sort of like everywhere, which are dense. Okay, so you can take Q here. Now Q is a countable set, right? Every rational number you can list one by one, right? You can list all rational numbers with in 0, 1 with denominator 1, with denominator 2, denominator 3. You can list them. You can list everything, right? I'm not asking for a list, but you can list it. That is okay. One by one, so you can recursively enumerate. If anything is in the list, it will come at a finite point. Yeah. Then it's very interesting, because then you are making, because the rationals are spread over, right? Whatever level you understand that, they are spread over. And then you can get functions which are not differentiable on all rationals and are convex. Okay. Okay, so these are the things, but let us come to the actual question. The actual question was almost differentiable. So we want to put, so we have kind of put a low, yeah, so let's just say simply, we want to put an upper bound on where all it can be differentiable. Till now, we are sort of, giving a bad name to convex functions. Okay, we're giving a bad name, but now we want to investigate a lower bound. Yeah, oh, sorry, an upper bound. Okay, so yeah, so these are like the worst kind of convex functions, not naturally occurring at all, but who knows? Yeah, maybe I should not say at all. Now let us put an upper bound, and the method that we will use here was also used earlier. Maybe for those who have written those mocks, maybe not all of you have written till there, so I'll not say at all anything about it, but others would realize it who have written it already. Okay. Convex functions are almost differentiable. Okay, so if we want to, let us just do it as an investigation. Yeah. So, sorry, why did I remove everything? No, so I can keep the definition, right? And I can remove these things. So what I'm trying to say is, see, in these kind of problems, what one thing that one can do when you, so usually the problem will be stated more clearly, but I'm trying to do it in exploratory ways. I'm not stating it, but we want to put an upper bound. We want to say that, it's not differentiable at so many places in some sense. Now let's see what it means. So to do this question, what we will do is let us fix a point of non-differentiability and investigate. Okay. Let f be non-differentiable at x naught. Yeah. Just fixed one x naught. Okay, we fixed one x naught in 0, 1. Okay, and x naught is here, and it is non-differentiable at x naught. Let us try to understand what we can say here around this point. Okay. Remember that the left, so this means again left derivative, okay, at x naught just means left derivative. So yeah, this exists. Yeah, this and this both exist. How do you convince us that that seems correct? Yeah, that looks correct, right? Okay, let's not, so don't prove it. I'll keep that as an exercise. Yeah, don't say the details. Yes, so try to prove that given any point, okay, given any point, the left derivative is less than or equal to, well, it cannot be equal because it's a point of non-differentiability. So strictly less than this. Okay, now for this, use the slope form. Use the slope form which we had used to prove differentiability, to prove semi-differentiability, and prove this. It's already clear the slopes are increasing. Try to prove this. Okay, so maybe I'll now ask someone else to try to take us forward. Okay, I think Raghav has given us a major idea here. So this is x naught, and this is what happens. And then what? Okay, someone else, please. Okay. So there is some sort of monotonicity in the derivatives, kind of. Okay, but for those who already know everything here, then don't say. Someone is struggling and trying it. Next time I will not give any overview. I'll just continue straight off. Okay. Today I plan to, but because I felt an overview was very important. Otherwise, it seems like what are we doing? Just but next time I just pick up from here and go systematically. So you see, you given a point where it is not differentiable. Yeah, the left derivative and right derivative, they have a gap. Yes, yes. Okay, since nobody. Okay, yes. So that is right. Yeah. So between this and this, you can fix a ration. You can call it cube x naught. Okay. Then what? Okay. So now you see, now if there is some other point where it is non-differentiable again, okay. So the point is that given any point of non-differentiability, we have isolated, we are kind of associating a rational number to it, okay. Sorry. Yeah. Now, if there is some other point, I don't want to call it x1, don't want to make it look like it's already a sequence. So let me just call it x. But anyway, let's just call it y naught, okay, because it's a point, right? Special point. So now you see, once again, you can understand this. left differentiable and right differentiable. Not just this, in fact, right? More is true. This is less than. This is again something that you can prove very easily using the slope definition. The slope definition is just a better definition for derivatives, right? Just write out the slope definition and just prove these things. Please do it. Even if you think I can do it, just work it out, because you may realize that there are some things. Okay, so again, this is true, right? So once again, we get another interval, and this interval is completely to the right. So this interval is, I'm just using this notation, okay? It's completely less than this. Is that right? Doesn't intersect, doesn't overlap even. Okay, because the slopes keep increasing, right? So the point is that at every point where there is non-differentiability, a lot of real numbers are wasted. This entire interval is wasted, right? And then the next point where there's again non-differentiability, the slope has to be more than this, right? So it cannot just keep, how much will it take? And then, yeah, and like this. So once again, you can find, yeah. So see, so basically the places where it is non-differentiable, we are associating some intervals to them. Those intervals are not on the x-axis and they're not on the y-axis either, right? They are in the, wherever you are tracking the slopes there, right? So you have these disjoint intervals. So for every, not writing this, for every point where it is non-differentiable, you have we have an interval, and these all intervals are disjoint. So how many intervals can you make? You can obviously make countably many intervals, right? You can list them, because if for every, I mean, simply put, you can just prove it like this. For every interval, I can put a rational, and for this interval, I can put another rational. It will be different, has to be different, and in this way, you know, you, because the rationals are countable, this is also to be countable. So this means that it's a countable set, okay? Countable set, listable set, or maybe in your, if you're for maybe it depends on the exam, you're right, it's just change in language, but the ideas will be this. Maybe they just say disjoint intervals or something like this, union of intervals, blah blah blah. Okay, but this is this thing. Okay, so any questions with what we have done so far? This is all I'll do for today. Okay, okay. So now there was another question which is not related to this topic. Okay, but yeah, but I'm not, so that's the question. So if you have this list of primes, so just maybe all of us can try this. I've not made any progress in this. I have a list of primes, goes on and on and on. Okay. We want to show that this is the list of primes, okay, 2, 3, and so on, 2, 3, 5, 7, and so on, right? Then we want to show that there are infinitely, I mean, this intuitively makes sense, but I don't know how to prove it. There are infinitely many n, okay, positive digits n, such that Pn minus k, the average Pn minus k and Pn plus k, was it greater than? Yeah, greater. Doesn't matter. Should be greater than, right? Okay. Yeah. So this happens, and not just for any k, but for all k less than n. Okay. So this is what we want to show. Oh yes, yeah, of course, yeah. This is Pn. Yes, right. Yeah. So what does its statement intuitively mean? That is very easy to see. So the point is that there are, so the point is that you keep encountering primes Pn, okay, such that when you look at all the primes to the left one by one, all the primes to the left from Pn minus 1, Pn minus 2 till P2, and you look at primes to the right till P2 and minus 1. Pn plus 2 dot till P2 and minus 1. You look at this thing, okay. Then the ith prime to the right of Pn, okay. The ith prime to the right of Pn, Pn plus I, yeah. And this gap is always bigger than the ith prime to the left, which may be Pn n minus I. Yeah. This gap will be bigger. This gap is bigger than this gap. That's what this statement is saying basically. Okay. It is intuitively basically reflecting the fact that as you go forward, the primes becomes more sparse, right? But how do you prove? I have no idea. I thought about this a little bit. What formula? Yes, there is, but that will not be useful. Yeah. And either ways, the proof of that is quite non-trivial. So yeah, I mean, one can definitely use some analytic number theory, but this is supposedly a easier one. But yeah, in any case, you can think about it using that. I don't know how to use that here. Yeah. But that is basically saying that if you look at pi n means the number of primes that are less than n. That is roughly equal to, if I remember correctly, log n. It should be, yeah. It's roughly equal to log n. As n becomes n by log n. N by log n. Yes. Okay, yeah. This is not elementary to prove, but the log n, or rather log n, I think is something like that. Something related is easier to prove. Yeah. Yeah, but this is obviously this is correct. Yeah, it should be n by log n. Yes. I don't know. Log n is too bad. Even Bertrand's postulate is saying log n. No, that is too bad. Sorry. This is correct. Yeah. So I don't know how to do this. I mean, infinitely many primes. So it must be induction. I don't think can be used, but it must be that you have to give it some form of prime maybe. But it's like all the way to the left. I don't know how to do that. If it is just 1 or 2 point, I will say. I mean, the typical n factorial thing and all works, but even those are open questions whether there are infinitely many primes of this kind or not. I don't know. I think those are open questions. I do not know. Anyone has ideas? Anyone has thought anything? Or you can just try this. I'll also think about this. Hopefully, I can do it if I think more. Hopefully, I don't know. But this is the problem. Okay. Yeah. Okay. So yeah, so this class was a bit late. So next time I'll start on time and I will start with the things, continue from where we left. Okay. Otherwise, please, all of you can all, we have a force, so we can all think about this and see if someone can do this. And maybe we can discover some interesting number theory through this, which where we can maybe use analysis or some complex analysis also. But yeah, let's think about this. Okay. So any questions about the class?